having said this, let us come to the second part of our lecture, which is on inverse response processes, right. So, what are inverse response processes? Let us first define it. Typically, inverse response processes occur when the output is actually produced by two effects. So, this is one effect which produces the output, and this is another effect that produces the output. They together produce the effect, overall effect on the output, and it turns out that one of them is opposing the other. So, you see, one is plus, another is minus. The second fact is that in the short time scale, that is over time scale, in the initial phases this one dominates, and in the long term this one dominates. So, when you have such a situation, then obviously in the short term you will get an effect which will come according to this one, and in the long term you will get an effect which will come according to this one, and they are opposing. So, the thing is that you why it is called an inverse response process, because the response to an input initially you see in an opposite fashion and finally you see in another fashion. So, if you design a controller for this process, then for the initial time scales this is going to be, the response of this will actually confuse the controller. This is, and might cause instability and other things. This is the main problem. For example, in this case, why is it supposed to be dominated by this initially and dominated by this later on? Opposing things is clear, because there is a plus and there is a minus. But how do we know that initially this one will dominate and initially that one will dominate? For example, the effect of this branch is to produce a negative output, and the effect of this branch is to produce a positive output. Now, we know that if you have a k2 by 1 plus s tau 2, then towards the initial phases, the response increases like a straight line whose slope is given by k by tau. So, during initial response, this block will produce a slope which will be minus k2 by tau 2, and this block will produce a slope which is k1 by tau 1, and this is k2 by tau 2. So, since according to this condition k2 by tau 2 is greater than k1 by tau 1, so therefore initially the response, now we can go to the next slide. So, what is going to happen is that so imagine that, let us consider this the step response of that process. So, I have given a unit step. So, the response due to the k2 block will start, it is very difficult to understand where to put it. So, the response due to k2 block will start along this way, and the response due to the k1 block will start along this way with this slope. So, the net result will be that the overall response will initially start going negative, and then it will change sign, and then it will settle at a level which is given by k1 minus k2, because those are the initial, because the response due to the k2 block will actually level, this will be the response. while the response due to the K1 block is going to be like this. So, eventually, and this is the overall response. So, see that the system will though if a positive unit step has been given, initially the system will show, for this time the system will show an inverse response, it will go in the opposite direction and finally settle down in the positive direction. This is what is called an inverse response. One thing we must note that the derivative of the response, this changes sign much earlier, it changes sign much earlier than the actually the response changes sign. This is a fact which is to be noted, which has some bearing. So, now having seen the kind of responses that we expect, let us at least see one example of why it happens at all. So, this is a very classic example of a what is this kind of process, inverse response processor, sometimes also called non-minimum phase systems. And this is a classic boiler drum level control, is one of the very classic examples of an inverse response process. You know, boiler drum means that all boilers, if you go to a power station, then what happens is that the boilers have tubes in them, and in those tubes water vaporizes. So, the water steam mixture actually goes and actually what happens is the water flows from a tank on the boiler, which is called the drum. So, let us get the picture. So, actually this is the container. On one hand the feed water increases, in fact there is another outlet of this which is not shown here, that outlet is here, and it is through this that the water flows into the boiler tubes. So, the water goes into the boiler tubes and returns, right. So, when it returns, it has lot of steam. So, water returns, this is the return, and this is the boiler drum level. So, this thing is called the boiler drum. It is basically a tank, which is a big horizontal tank situated right on top, very high above. I mean, typically a power station boiler is about 3 stories high and the drum is on top of that. If you want to see it, you have to go up a number of stairs. So, what happens is that, without going into much details of boilers, let us see what happens is that the water enters here. Here there are lots of bubbles, steam bubbles, which actually come to the surface being lighter. They come to the surface and then they break and then they form a steam part in the boiler, which eventually goes out and finally goes through the superheater and then enters the turbine for power generation. Now, imagine, so in the steady state what happens is that the mass, if the boiler drum level has to be maintained, then the mass of feed water the mass of water that is entering the system and the steam that is leaving the system must be matching. So, what happens? Now, imagine that the power station operator wants to increase the power. So, he will do what? So, for increased power you need to supply increased steam to the turbine. So, the steam flow rate will be changed. So, when the steam flow rate is changed, immediately what happens? See, what should happen in the steady state? What should happen? In the steady state, what should happen is that that is also shown here, that in the steady state steam flow rate is increased. So, steam flow rate is actually greater than water flow rate. So, there is a material imbalance. So, eventually this this drum level finally should start falling, because less material is entering and more material is leaving the system. This is going to happen in the steady state, but what happens in the short range? In the short range, what happens is that immediately when the steam flow rate is increased, there is a reduction in pressure. The pressure falls. Now, you see that what the crux of the matter is that this level is here, there are bubbles, these are steam bubbles. So, the volume occupied by the steam bubbles actually depend on the pressure which is applied on the surface. So, the moment this pressure will be released, these bubbles will expand. So, this expansion of steam bubbles, which will mean that this volume will rise, volume will go up. So, you see that here you see a non-minimum phase response, that is in the long range the volume should start falling, but in the short range what will happen is that it will go up. This is non-minimum phase behavior. This is shown in various other cases, in aerospace plants also such a thing is shown, but anyway. So, now what this causes, so let us look at the thing a little analytically also. So, you see that if you just see the feedback transfer function and do a little analysis, we will find that the y feedback was the point where we were adding that Smith predictor output. So, this was y and this was that g into 1 minus e to the this is not that one, this is this was yeah. So, basically this says that simply this is nothing, sorry we are not yet considering feedback at all. So, this is nothing but the open loop output. For example, let's go back a little bit. So, this is nothing but the response to this one. So, the response to, simply if you calculate y, it will come out to be that expression, right. So, correct. So, this is simply the open loop transfer function. Now, what we found that, you see, k2 tau 1 is actually greater than k1 tau 2 from this expression. So, therefore, this is actually a negative quantity, less than 0, and this is a positive quantity, greater than 0, because k1 by k2 is greater than 1. So, what happens is that we have a fact. So, we have terms like, you know, A minus Bs, which means that it has a 0. The poles are this will give the poles and this will give the 0 of the transfer function, that there is a what is known as a right half plane 0. So, the real part of the 0 is in the right half plane, and such transfer functions are called non-minimum phase for a different reason, which is not concerned, we are not concerned with that. So, we will not try to explain that, and that 0 location is given by this minus k1 by k1 minus k2 by k1 tau 2 minus k2 tau 1. So, that is the location of the 0. Now, the question is that it is this opposing effect which is causing this inverse response and which is also causing the 0. So, the question is that how can we remove this non-minimum phase behavior? Why we should remove it, that we will also see, but this non-minimum phase, we can at least understand at this point of time that the controller is going to get confused, because the controller has been designed for the final response, which should move in a certain way. Initially the response is going to move in a different way. So, the controller will tend to give a different kind of controller will get confused in driving the plant. So, now the question is that so perhaps we should remove this non-minimum phase 0 and somehow put a minimum phase 0. Now, how to do that? This is not, for example, we know that if we have, with the kind of transfer function that we have considered till now so far, generally also in first level control courses, they always have the poles. Let me choose color. So, the poles can be if they are in the left half plane, then stable. If they are in the right half plane, unstable, and we by feedback we have seen using a controller we can bring it from right half plane to left half plane. But what do we do about zeros? One very standard way of changing zeros, suppose a transfer function has s plus a by s plus b, that is, it has the left half plane 0, and we want to change it to, we want to make it to s plus c by s plus d. So, then what do we do? So, we can always multiply it by s plus c by s plus a. Suppose this is we are talking about zeros, so let this be b only. So, if you want to change the 0, we can always multiply it, so that this and this will get cancelled and we will get this. But this is not possible when you have a right half plane 0, because if it is s minus a by s plus b, then you cannot multiply it by s plus c by s minus a and say that this is cancelled and it will give you this, because this transfer function is unstable. So, what this is going to cause is, it will cause, and if you try to do it like this, it will cause what is known as internal instability. So, what happens is that internally some signal will go unstable, although it may not affect the output. So, we cannot cancel the 0, you see. So, what we must do is, so what do we do? So, this is another case where we are saying, so actually now we come to the control problem. What happens in the, let us say for example, if you have a PI controller, then the PI controller will apply some input in the right direction, when it will change see the set point coming, but the error does not decrease, because the error goes in the opposite, because the response goes in the opposite direction. So, the error does not decrease, but it increases. So, what does the PI controller do? It applied more input. It thinks that, oh, it is not going, so let me apply more input. So, the more the input is applied, the more inverse response will come, and this might lead to an unstable situation. On the other hand, if you have a PID controller also not only sees the error and its integral, it also sees the rate. Now, as we have seen that the rate will reverse quicker. So, the PID controller is likely to give slightly better response, because it will try to give correct inputs much faster because of the derivative reversing. So, this is just an aside. But let us see first how we can compensate for this inverse response. So, first, what is the requirement? The requirement is that in the steady state, my response should be all right. So, this whatever compensation I want to do, its effect in the steady state should not be there. But in the transient response, actually what it should do is this inverse response, it should not allow to be fed back to the controller, which is confusing the controller. This is the main thing. So, it should remove the inverse response from the feedback in the initial parts. Now how to do that? So, to do that we have this. So, you see again just like Smith predictor, we are again adding another term here. So, this, let me select this. So, again adding another term here. Now, what is the effect of this term? The effect of this term in the steady state, the effect of this term you can verify is 0, because 1 by 1 plus s tau 2 and 1 by 1 plus s tau 1 set s to 0, the steady state gain of this is 0. So, in the steady state no effect, but in the transient what happens? So, now the plant is seeing this feedback rather than open loop response feedback. I am now modifying the view of the plant. So, what happens is, now the feedback term if you calculate, then you will get it as k1 tau 2 minus k2 tau 1 plus k into tau 1 minus tau 2. So, this term has been added now. Previously it was only this and it was negative. So, if we want to shift the 0, then what we have to do is we have to add this k in such a manner that k is greater than or equal to this. Then what will happen is that this 0 will become a left half plane 0 and the non-minimum phase response will not be shown to the controller. So, the controller will not see the non-minimum phase response and will not get confused. So, this is the approach which is taken for non-minimum phase systems. So, this is the way that we are now coming to the end of the lecture and we have to quickly review the lesson. So, first we saw the sources of time delays and their effects on stability, and then we saw a way of controlling by Smith predictor controls. We did exactly the same thing for inverse response. We saw inverse response, how it arises in a process and its problems, and finally we saw a way of inverse response compensation. To end the course, to end the lecture, we have as usual some points to ponder. So, you can describe 2 typical sources of time delay in example industrial processes. You give your example, explain why time delay degrades stability, try to understand it, draw the block diagram of a Smith predictor. This you should be able to do after this lesson. The step response for an inverse response process, and finally the block diagram of an inverse response compensator. So, that is all for today. Thank you very much.